Okay, so last time we discussed matching in bipartite graphs, and we discussed Koenig's theorem. So Koenig's theorem says that for in bipartite graphs, minimum cardinality of vertex cover is same as the maximum cardinality of matching. Okay, that we proved last time. We also see a characterization for matching by augmenting path. Okay, so any matching given a matching is maximum matching if there is no m augmenting path, and converse is also true. Okay, so yeah. So let's talk about something perfect matching. So what is perfect matching? So given a bipartite graph, and in fact it is for general graph. So a matching is called perfect matching if every vertex is saturated by the matching. Okay, so every vertex is matched. So a matching M such that every vertex is matched with respect to M. Okay. This is also called one factor. So in this book it is called as one factor, and so let's define what is k factor. So k factor of a graph. So k factor of a graph is a k regular spanning graph. Okay, k of a graph G is a k regular spanning subgraph. So what is one factor now? One regular spanning subgraph, right? So one regular spanning subgraph is a matching. What is two regular spanning subgraph? For any G, what could be the two regular?
One factor k factor should cover every vertex.
Yes, because it's a spanning subgraph. So two factor would be two regular spanning subgraph. That means union of cycles. Okay, so yes, spanning subgraph. So yeah, cycles, disjoint cycles. Okay, so in bipartite graphs, what can we say about? I should not have removed it. Okay. So in a bipartite graph, what can we say about perfect matching? What would be the necessary condition? What can be? So you have given a bipartite graph. So for a perfect matching, what should be there? Right? So to have a perfect matching, at least cardinality of A, cardinality of B should be same. Okay? So that is a necessary condition, but it is not sufficient, right? So this is not sufficient that they have same cardinality, but okay, something like this. So we can write it as okay, A. And what is B? B is actually, we can say that it is neighborhood of A, right? B is a neighborhood of A for whole set. Neighbors are in B. Yes, this is necessary, but not sufficient. Okay, so let's think if we don't have, like, these cardinalities are not same. So then can we say something about, like, about a maximum matching which saturates one part? So say that cardinality of A is, if cardinality of A is strictly less than cardinality of B, then it has started now.
Not started or nobody joined, right?
So nobody joined.
But I think we got some text.
Yeah, in the group people have texted there are no Zoom is not started.
Zoom is not started actually. We thought
Oh,
One.
okay.
No, I started already.
So maybe some different link that.
but there are some problem. Yes, there are so many actually.
Ankit, am I audible to you?
Yes, you are audible to me.
Okay.
You can just
Yeah. So okay, last time we started matching, and we gave a characterization for matching by augmenting paths, that if a matching is maximum matching, and if and only if there is no m augmenting path in graph. Okay, and we discussed matching in bipartite graphs, and we talked about Konig's theorem, which says that maximum cardinality of matching is same as the minimum cardinality of the vertex cover in bipartite graphs. Okay, so now we are discussing this time we will discuss perfect matchings and Hall's theorem. So first start with perfect matching, and perfect matching is a matching where every vertex is saturated by m. Okay, this is also known as one factor. So for that, let's define k factor. So k factor of a graph is a k spanning k regular spanning subgraph. Okay, so so one factor will be one regular spanning subgraph. That means the set of edges, independent edges, is the spanning subgraph, which is a perfect matching, because it says spanning. So that means it covers every vertex. So this is a perfect matching. One factor is a perfect matching. Okay. Now we are looking at the some necessary condition for perfect matching. So in bipartite graphs, if you want a perfect matching, then what should be the cardinalities of A and B? So they should be same, right? So to have a perfect matching in a bipartite graph, the cardinality should be same. But this is only a necessary condition, but not sufficient. Okay. Now I am saying that if suppose the cardinalities are not same for these sets, so let's cardinality of A is less than cardinality of B. So now can we say something about the maximum matching, sorry, not maximum matching, but a matching which saturates one part? Obviously that will be maximum, but yeah. So can we say something about that? So if so if A is less than cardinality of B, then can we have a matching which saturates B? So now notice that this is not enough that B's cardinality is greater than A. So we can match every vertex in A. It is not necessary. Okay. Sorry, it is not sufficient, it is necessary. So this is necessary to saturate A, that cardinality of B is greater than A, and B we can look at it as neighborhood of A, okay, because every neighbor is in B, right. So we can write B as neighborhood of A. So this is necessary, but not sufficient. And maybe we can see some example here. Yeah, perfect matching means that both sides should be there, but now I am saying that suppose if cardinalities are not same, then can I make sure that there exists a matching which saturates one part, and of course smaller part, because you can have a matching with the cardinality of the smaller part. So, let us see some example. Okay. Something like this, and maybe right. So, for this graph, neighborhood of A, cardinality of neighborhood of A is greater than cardinality of A, but it does not have a matching which saturates A, right. So, this is not sufficient, that means. So, what can we change in this? If we say that for two vertices, so for one vertex at least one neighbor is there in B, right. If I say that for two vertices A and A prime in in A set, if its neighborhood, so say S, if neighborhood of S has more vertices than S, so can we match it? Like, we may be able to, like, right. So, because we are saying that we have A prime, and they have at least something like this, at least two neighbors. Okay. So, basically I want to give this condition that if we take any subset of A and we look at the neighborhood of this set S, neighborhood of S. So, if I say that neighborhood of S is at least the cardinality of S, then this is necessary, right. This should be there to have a matching to saturate A, right, and right, this is true. Not sufficient means if you have any condition is when it is sufficient. When you are saying that okay, this condition holds, then can I say about the matching that it must exist? So, that is the sufficiency. Necessity is when we are saying that if we want a matching, then this should be there, this must be there.
I know. So I'm saying that if graph G has the perfect matching, bipartite graph, if and only if the cardinality of both the partition is
No, I am not talking about perfect matching. I am saying cardinalities are not same now. So, I cannot have a perfect matching because cardinalities are not same. But I am asking that if I can get a matching which saturates one part, smaller part of the bipartite graph. Yeah, of course, smaller part you can get matching, right. We cannot saturate B whole graph like whole part B. Okay. So, we have taken this condition when cardinality of A is less than cardinality of B, and then we are asking, does there exist a matching which saturates the whole set A. So, we are looking for condition for this matching which saturates A. Okay.
that if cardinality of A is less than cardinality of B, and to saturate A, if we take any subset of A, its neighborhood, size of its neighborhood should be at least the subset we have taken.
Yes. So, for first we checked for whole set. So, for whole set is like trivially it holds, like, so it is necessary, but it is not sufficient because we saw it here that if you even if you have B with a large size, then and A is very small size, still you may not be able to cover all the vertices in A. Okay. So, this is not sufficient. Because you are saying here that cardinality of A is less than cardinality of B. Okay. Yeah, so so cardinality of A is less than neighborhood of A, right? So this holds for whole set because neighborhood of A is exactly B, right? Set. Yeah. So I'm saying that this condition is there for whole set, but it is not sufficient for me because I can see that clearly that if you even if you have very small set A and B is very large, still you may not be able to get a matching. So for example, this graph. So you can have this vertex of very high degree and B size can be anything, but still and A size is only 3, but still I won't be able to match A, like have a matching which saturates A. Okay, so I want to put like some further condition to make sure that it has some matching which saturates A. So I am refining this condition, you can say that, okay, I am saying not for whole set, but for every subset of A, this condition should hold. If I am saying this, so this should hold to have a matching. So this is necessary. This is necessary, right? If for some set, if you don't have this condition, can you have a matching which saturates? No, right? Because if you have some subset S such that its neighborhood of S cardinality is strictly like less than cardinality of S, then how can you match? So in S you have 3 vertices, in neighborhood of S you have 2 vertices. So how you will match S? So you won't be able to match. So that means this is necessary. Okay. Now we want to see whether this is sufficient also. Okay. So this condition, we are saying that neighborhood of S is at least cardinality of neighborhood of S is at least cardinality of S for every subset of A. So this is a necessary condition. Okay, and we want to see whether it is a sufficient also, and in fact this condition is sufficient as well. So we can say that there exists a matching which saturates A if and only if this condition holds. Okay. So this is the theorem. And we are in bipartite graph, so this we are doing for bipartites. So G has a matching M which saturates A. If and only if neighborhood of S cardinality is at least cardinality of S for every S subset of A. Okay. So one side is okay, right? That is because necessary condition. We need this. So we want to prove the sufficiency of this condition. Okay. So so given that your graph satisfies this condition, we want to prove that there is a matching which saturates A. Okay. So how can we start with? We'll say that okay, we have this condition, and so let's suppose there is no matching which saturates A. Okay. Okay, so let M be a maximum matching, and we know that this condition holds, and right now we are assuming that there is this M does not saturate whole A. Okay, so what does it mean? I have a matching and it does not saturate whole A. That means there exists some vertex A. So there exists some vertex A in A such that A is unmatched. So this vertex A is unmatched, but it has some neighbors, right? Okay. Let's make some graph. Okay. Like this. So if B is unmatched, so A has some neighbor by this condition. You can take S as a singleton. So A has some neighbor. So this is B, its neighbor. If it is matched, if it is unmatched, then what happens? Yeah, we can add this, right, if it is unmatched. So, and actually we started with maximum matching, so that means it is not, or not maximum matching, you will say any matching. Okay, so we start with this, and okay, so that means this is matched. So this is matched by some H here. Now, so like this we have some matching. Okay, okay, this is some matching. So let's define a set A prime. A prime has those elements in A, those vertices, such that there is some M, there is a M alternating path and at A. Yeah, that is what we are doing actually. So, we want to extend this matching, and then we will say that we contradict, because yes, we started with maximum matching. Okay, so, we want to extend this matching. How can we extend this matching? Last time we saw the characterization for augmenting path, right. So, if we can extend it, that means there should be some augmenting path, and we know that A is unmatched. So, we want an augmenting path from A. Okay. So, because we are assuming now that this is maximum matching, and so we will look any alternating path. Now, first vertex is unmatched, right. So, I am taking all the vertices in A which has some M alternating path to this vertex A. Okay. So, I am collecting all those.
For an M augmenting path, you need at least two unmatched.
Yeah, I am taking alternating path.
Yeah, I mean not related to this definition.
Okay.
For M augmenting path, you need at least two unmatched vertices, right?
Yes, yes. Then only you can extend. If only there is one unmatched vertex in your graph, that means you cannot match it with anyone. So, that is in fact your maximum matching, whatever you have. Okay, so, so we are looking for some augmenting path here. Okay, so this is our A set. Now, because we know that, okay, let's define B prime as well. So, B prime has all those elements which contains in some of these paths, okay, any of this path. So, B says that V belongs to some alternating path, M alternating path. to A. Okay. So, B prime is those vertices which belongs to these alternating paths. Okay. So, now look at their cardinalities. What happens? So, we have some here A prime, some B prime, and A is not there. I am assuming A is here. Okay, I should draw some other picture either. Okay. Okay. So, like this. So, what can we say about these two cardinalities? We know that in A prime, this edge is matching edge, right?
Wait 1 second. How you define A prime to be this prime?
A prime, if there is some M alternating path and set A.
And then what is A? That A? Like
That A is that we started with some unmatched vertex.
no, but I don't understand.
So, so we have this some unmatched vertex
Yes.
A. So, I am just looking at alternating paths
Yes.
coming to A. Okay.
Then how you define those vertices in A? That
Yes.
are in that alternating path.
Yes.
Okay. So that
Okay. So, this is unmatched. So, first edge which is going, that is unmatched, that is not in matching. Now, this one is in matching, then this is not in matching, this is in matching, and now these endpoints I have taken in A prime and these I am taking in B prime. So, there are many alternating paths. Okay, there might be many alternating paths. I am just collecting all those vertices in A prime and all those vertices which belongs to that path in B prime. Okay. And now notice that because it is alternating path, then last edge of the path should be in matching, right? Should be matched.
alternating path should start with an unmatched vertex, right?
Yes. So, we are starting here.
But they end that way. No, that is same na, starting or ending.
Yeah, you can say starts at A. Okay. So, this alternating path should end with the matching edge, otherwise you have alternating path already, right. So, that means because always you are entering with some matching edge in A prime and then going back and then coming back to like with some matching edge. So, that means, and we have defined A prime first. Okay. So, we are looking at the alternating paths from set A. So, that means this cardinalities of A prime and B prime are same. Is it okay? We have defined A prime first. We are saying that A prime has all those vertices which has some M alternating path which starts at A and ends at this vertex.
A excluding A.
Yes. So, like this vertex has alternating path to A, right. So, this is an A prime. So, like every vertex which has some alternating path to A, I am putting that in A prime. All those vertices of B which belongs to some alternating path, I am putting in B prime. Now, I am saying that their cardinalities are same. Is it okay? Because in set A prime, A is not there, okay, A is below. So, whenever you are coming in A prime, you are coming with some matching edge, okay, from this path. And then when you are coming lastly, then also you are coming with some matching edge. So, last edge of your alternating path should be in matching, okay, because you have defined A prime as that your path ends at here, okay, whatever vertex has alternating path up to A, I am putting in A prime. So, that means that vertex should be matched by some matching edge. Okay. So, that is why now if you have a matching, so every vertex in A prime is coming via some matching edge. So, that means their cardinalities should be same, right, because basically you have a perfect matching here in between A prime and B prime. Okay. So, their cardinalities are same. Now, look at this set. What about
But one alternative path can also end with a non-matching edge.
yeah, then it will become an augmenting path.
We started with a maximum matching, so we assume there is no augmenting.
Yes. Also, by this definition, this should be like this is non-matched. Na? If there is no matched edge on this vertex, that means here itself you are getting some augmenting path. So, whenever I am coming via some non-matching edge, then that vertex should be matched. Okay. So, now look at this set A prime union A. Okay. What is its neighborhood? So, its neighborhood cardinality should be at least the cardinality of S prime, cardinality of S, because we assume that we started with that, okay, that holds conditions is true. So, for this set as well, neighborhood of S cardinality is greater than cardinality of S. So, that means there exists some vertex outside B prime which is neighbor of some of these. Okay. So, that means there exists some B outside B prime which is neighbor of some vertex V in this set A prime union A. Okay. Because this implies there exists a vertex So, in S there is some vertex V which has neighbor B. Now, what about A to V? We have a path A to V because V in A prime or either V is exactly A. So, if V is exactly A, then okay, you have A B H, or otherwise from A prime you have some vertex which is adjacent to B. Okay. Okay. So, what we are saying? So, what can we say about B? If B is matched, what can we say about B? If B is matched, then what can we say? Yes, if B is matched, then B should be in B prime, right? So, if B is matched, then B should have been in B prime, but we picked B from the outside B prime. So, this can't happen. So, that means B is unmatched. Okay. So, if B is unmatched, then are we done? Right? Yes. So, we got some augmenting path. We start with A, go to V via alternating path, and then B to B. So, if your path was like this up to this vertex and then V2B. So, we got some augmenting path. So, that means yeah, it contradicts the fact. Okay. Any doubt in this? I don't think so. Okay, let's. So, we can prove this theorem like multiple ways, like sufficient condition. You can also prove by induction. Okay. So, I will give one more proof, not by induction. Induction you can try. So, I'll take. Okay. So, we know that now our Hol's condition satisfied. Okay, and we want to prove that there is a matching which saturates A. So, we will look at all the graphs which satisfies the Hol's condition, right, and we will take the minimal edge subgraph, minimal edge subgraph. So, we start with the let H be a minimal edge graph which satisfies Hall's condition. Okay. So, what can we say about this graph? If it is minimal edge graph which satisfy this condition, that means their neighborhoods should be same, right, for every vertex. And what does it mean? That you have some vertex in A, then its neighborhood is at least, it has at least one neighbor, right, according to Hall's condition. But because I am taking minimal edge graph, then in that graph it should have only one neighbor, right. So, if we able to show that for every vertex there is only one neighbor in B, then we are done, because that means we have a matching itself. H is a matching itself which saturates A. Okay. So, that we want to prove. So, given this H, a minimal edge graph which satisfies Hall's condition, we want to prove that for any A belongs to A. We are not talking about B because cardinality of B is more, but yeah, even number of edges we can count. Okay, we are not looking at that, but for every A in A, we want to prove that in H degree of A is 1. If we able to prove this, then we are done. Okay. So, let us see what happens if degree of A is not 1. So, let degree of A in H is at least 2, okay, and we picked the neighbors of A in H. So, suppose A has two neighbors now, B1 and B2. Okay. So, we can see that if we remove A B1, then Hall's condition should fail, right, because this is H is a minimal edge graph which satisfies Hall's condition. So, that means if I am removing any edge, then Hall's condition should fail. So, okay, I will just remove this edge. So, I will take a subgraph H1 while by removing an edge AB1. Okay. Similarly, I make another graph subgraph by removing H A B2. Okay. So, now for these graphs Hall's condition should not satisfy. Okay. So, so suppose it does not satisfy, then what can we say? So, we have now two graphs. So, let us pick some. It does not satisfy Hall's condition means we say that this both does not satisfy Hall's condition. What does it mean that H1 does not satisfy Hall's condition? Yes. Yes. So, there exists some subset of A. Okay. So, let us look at some subset A1 which contains A, and say this is its neighborhood, and for H2 as well we can pick, we have some set A2 and A is common in both sets. Okay. So, there exists some A1 such that cardinality of A1 is strictly greater than neighborhood of A1. Okay. And similarly, cardinality of A2 is strictly greater than neighborhood of A2. Okay. So, if cardinality of A1 is greater than, okay, so for these two sets Hall's condition fails. Now, I want to show that even in the graph H, I could find some set which fails Hall's condition, then I will contradict the fact what I took, right, then we will get the contradiction. So, I want to do that. So, what should I take which is in H? What we can take? We can take the intersection, but it should not contain A, right, because of A only we are saying that in A1 does not satisfy Hall's condition now, because I have removed some H from A incident on A. So, that is why in my third set with which I want to like give contradiction, A should not be there. Okay, then I will say that okay, this subset was in H as well, and now it fails the Hall's condition. So, I will take A1 intersection A2 and remove the vertex A from this. Okay. So, I am taking this intersection and removing A from this, because then this for all these vertices, this set, this is a subset of H as well, right, because I made changes only on the vertex A, I removed some edges incident on A, but not in this set I have not removed anything. So, it was present in A as well. So, if I can show that for this particular set Hall's condition fails, that means my H did not holds the like Hall's condition. Okay. A was the part of H, but now I am removing from this set, because I want to show that these edges like these does not affect this set. I want to take this set because, so what I said, like I said that okay, A has two neighbors B1 and B2. Now, I am taking two graphs. In one I am removing A B1 edge, in second graph I am removing A B2 edge, and now I am saying that okay, now Hall's condition fails, because we started with a minimal edge graph. Okay, we satisfy Hall's condition. Okay, so, from there we took A1 and A2, that because for now H1 and H2 Hall's condition fails. So, there exists some set which fails this Hall's condition, and that Hall's condition fails on that set because of A, right. So, because of A only on A1 and A2 it fails. So, now in this graph if I can show some set which fails Hall condition and it does not contain A, then that means that set does not hold Hall's condition in H as well in my original graph, which is a contradiction, right. So, that is why I am taking some subset which does not contain A.
So, what if A1 intersection A2 is just
If A1 intersection A2 is if it is empty, if A is the only one in both, then one second. Then for this set, what you can say, this holds.
So, if the intersection is only A, then the neighborhood of A is B1 and B2.
Yes.
You can remove AB1 or AB2 and still the Hall's condition is satisfied and we get getting a number.
Yes.
So, in that case it is
Yeah, it is obvious. Okay. What I have problem is that if we say that A is the only one in intersection A2.
So, removing one is AB1 or AB2 violating the Hall's condition, and if the only intersection only contains A, then that violating set must contain A, and if it is only contains A, then and we know that there for A it is not violating.
Yeah, that what you are saying, that is correct, but what if you can say that here as well, what is the difference? Like in the starting, you could say that you have this A degree 2 vertex, but from that you can remove one of the edges, and but can you say that?
Then it
We
is
don't know.
Still, if it is still holding, then it is not age minimum.
Hmm?
If the Hall's condition removing after one is
Yes, but that we have to check, right, that after removing one edge, Hall's conditions are like they hold or not.
that is why we are doing this thing.
But
Yes.
saying the minimal edge graph.
Yeah, minimal edge graph.
So
Yeah, so but we have to show that Hall's condition now does not hold, or it still holds. Yes, we have to show that it still holds, and then we can say, okay, this was not like best choice. This was not we picked.
so once again, so minimal edge graph which satisfies Hall condition means if we add another edge, then it will not satisfy Hall condition.
No, if you remove one edge, then it does not satisfy hold condition anymore. This is not maximal, this is minimal. Yeah, after that every vertex, like after adding an edge, maybe every time you may satisfy Hall's condition, but if I remove any edge, then it won't, it will not satisfy. So, that is what we are showing now, that if you remove one edge, then Hall's condition fails somewhere, and by doing that we just want to construct a set which was present in H as well. That means it does not include A, and that fails Hall's condition to contradict.
As he suggested, I think it's right that if A is the first one you have started with and A1 intersection A2 is A itself, then of course in the original graph you started with doesn't hold the Hall's condition.
So if this intersection contains only A, then remove that thing from intersection. It reduces the size of this set by 1 and reduces the size of this set
Yes,
by 1.
yes, and this set is
Still it is violating Hall's condition. So in original graph there is a set subset of this thing.
yes, yes, yes.
Excludes A and still. Yeah.
Yeah, this is correct. Now this is correct. If you are saying that if in this intersection only A is there, what we wanted to contradict our assumption, we wanted to say that we want to find a set which was present in H as well, and that fails Hall's condition. Okay. So, if A is only here in A1 intersection A2, then this set fails Hall's condition, right. So, this and this is in H as well, because A is not present here in this set. Is it okay? Everyone seems very confused. Okay.
Hi, Shaily.
Yeah. Yeah, Ankit.
I'm confused in the very first line actually, and I'm confused with the proof strategy actually. This
Okay.
counterexample by the contradiction. What does it mean actually? What is the intuition behind to take such kind of a graph? And so I'm confused here at that point of time, at that place.
Okay, okay. So, I will start again. So, I am saying that I want to say that I am in the reverse direction, right. So, I have a graph which satisfies Hall's condition, and I want to prove that there exists some matching which saturates A. So, now among all those graphs on n vertices, I am taking a graph with minimal edges, with minimum number of edges, which satisfies Hall's condition. And if I can show here that for this graph, yes, so for this graph, I am showing that there is some matching, and no, sorry, one second. Okay, so what I want to show that I have started with some H with which is minimal edge graph which satisfy Hall's condition. So, now Hall's condition, if you look at the Hall's condition for one vertex, okay, singleton set. So, for one vertex only one neighbor is enough, right. So, if I say that for every vertex in A there is only one neighbor, then we are done. This graph, yes, if I say that for every vertex degree is 1 and it satisfies Hall's condition, it satisfies Hall's condition means that for every vertex A I have some neighbor, then we can say that we have a matching. Okay. So, your H itself is a matching. So, that I want to show that minimal edge graph is a matching which saturates A. So, I started assuming I want to show this that degree is 1 for every vertex A in A. So, I started with that contradiction, that suppose there is some vertex which has degree at least 2, and so it has two neighbors B1 and B2. Now, I will make two subgraphs out of this edge. I will remove one edge AB1 and make one subgraph. I will remove one other edge AB2 and make other subgraph. So, now these are subgraphs of H, and we started with a minimal edge subgraph which satisfies Hall's condition. That means, these subgraphs should fail Hall's condition, right. So, there must exist some subset of A in H1 and H2 which fails Hall's condition. Okay. And now, I am taking those two sets and somehow I want to construct a set in H1 which is which belongs in H as well and which fails Hall's condition. That will be my contradiction.
It's fine.
Okay, and then we can say okay, for every vertex degree is 1, and so we are done. So that is what I am doing here. So I have these two H1 H2 subgraphs which I have make from this after removing one of the neighbors of A, one of the edges incident on A, and now I am saying that because H1 does not hold fails Hall's condition on some set. So, that means there exists some subset A1 of A which fails Hall's condition, and similarly in H2 some set A2 fails Hall's condition here. Okay. Now, I want to make a subset of A which fails Hall's condition and which is also present in your original graph H, and that means you it contradicts your assumption that you started with the graph which satisfies Hall's condition everywhere. So, this is my that set A1 intersection A2 set minus A. So, this is my subgraph of H, and I want to show that neighborhood of A1 intersection A2 minus A, its cardinality is so I want to show this, okay, that this set fails Hall's condition. Okay. So, let us start with this. So, what is its neighborhood? Its neighborhood is some B1. So, this is some B1 plus some, okay, right. Now, B1 plus cardinality of B1 plus cardinality of B2 minus cardinality of B1 union B2. So, this is as cardinality of B1 intersection B2. Is it correct? I started with right thing, right? Okay. Now, what can we say about cardinality of B1? This is neighborhood of A1 is B1, neighborhood of 2 is B2. So, cardinality of A1 is strictly greater than cardinality of B1. We started with this, and that means we can say cardinality of B1 is at most cardinality of A1 minus 1. Similarly, cardinality of B2 is at most cardinality of A2 minus 1. So, from these conditions, so what I will get here, it is, let us put it here, this A1 cardinality of A1 minus 1, cardinality of A2 minus 1. What about B1 union B2? What would be its cardinality? This is the for A1 union A2. Neighborhood of A1 union A2, what would be the neighborhood? This would be the set B1 union B2, right? So, this is neighborhood of am I doing it correct? A1 union A2. I will just take
So this thing A1 union A2 is violating Hall's condition. So B1 union B2 should be at least.
yeah B1
Then
yes B1 union B2 should be at least, it should be here that B1 union B2, this should be at least cardinality of A1 union A2, and just like -2, and what is this? This is cardinality of A1 plus A2 minus cardinality of A1 union A2. That means it remains with the intersection A1 intersection A2 -2, and now this is sorry यहाँ पे आएगा, this is less than equal to, we started here, so we have replaced okay. So this is A1 okay, and this is A1 intersection A2 -2. So I can say that the cardinality of A1 intersection A2 set minus A, cardinality -1, right? This is same as this, and now this is strictly less than cardinality of A1 intersection A2 set minus A. Okay. So we are done, right? That's what we wanted to show, that this set, this is a subset of A in H, and this fails Hall's condition because its neighborhood has less cardinality than the set itself. Okay, so this is a contradiction. So we started with some sets that Hall's condition fails in H1 and H2 because we removed some H, and then we found sets A1 which fails Hall's condition in H1, A2 which fails Hall's condition in A2 in H2, and then we construct a set A1 intersection A2 and set minus A, and this set also fails Hall's condition. We have showed that. Now notice that this set has the same neighborhood in H also. So that means it fails Hall's condition in H as well. So which contradicts our assumption that H satisfies Hall's condition. Okay. Is it clear now?